All right, we're going to start our first Coriolis problem, and a merry-go-round is a really good excuse for our first example. So what I have here is we have a merry-go-round, so this will be link 2. This is the thing that's touched everywhere. Here we have the person walking the path. So they're touched in one spot, their feet. Suppose that person walking the path is you. So we know what the merry-go-round is doing. It's spinning counterclockwise, so we have zero point 0.5 radians per second, and it's speeding up. Alpha is 0.2 radians per second squared. Now, with respect to the path, the velocity relative to if somebody was sitting here watching you walk, your velocity as you walk along this path is absolutely constant, 0.75 meters per second. All right? So you're going to be, and here's your path. You're going to walk along a straight line, 1 meter off of the center line of the merry-go-round. Then you're going to take a circular path at constant velocity until you get over to here. Then you keep doing it. Okay? And the radius of the circular path, 3 meters. All right. So noting what link 2 and link 3 is, this is really just plug and chug. Because we know everything about what the merry-go-round is doing. So what we simply have to do is go to the point we want to figure something out. And what are our points? Points C and D. So I want to get, at this point, I want to figure out what the merry-go-round is doing, and then jump to you, the person walking. Likewise at D, figure out what the merry-go-round is doing, then jump to the person walking. So let's start. At C. So what is C doing on the merry-go-round? Well, it's just omega cross R. We know omega. And R is just minus 1y. This is the relative term. If somebody's laying down and viewing the merry-go-round as if it's on ground, what do they see you doing? Well, they see you walking to the right here at 0.75 meters per second. So that's 0.75x. That's their perspective of what they see. All right, so let's just take that. So here's omega cross R to get C on link 2, 0.5z minus cross minus y. Then here's our relative velocity, 0.75x. Add them up, done. 1.75x meters per second. Let's do D. So what's D doing? It's omega cross R, where R is now minus 3 meters. We see that here, 0.5z cross minus 3. But because of the path, it's now minus 0.75x. Okay, add it up. We're done. 0.75x meters per second for D3. All right. So now we've got the velocity stuff. Let's go figure out the acceleration of C3. Okay. Here's the basic equation. It's the acceleration at C of the merry-go-round plus these two Coriolis terms. Okay. So we'll apply that. The acceleration of C on the merry-go-round is alpha cross R minus omega squared R. That's right there. So we know all that information. OC is just minus 1y. And we know alpha 2, omega 2, plug them in, done. Now we have these terms. Plus 2 times this cross product. Omega 2 is the merry-go-round because it's touched everywhere. Cross that same VC3, VC2 we had a little moment ago. Okay? Well, we know all those terms. When you do Coriolis, this term is always known. If it's not known, you screwed something up previously. Then we have the relative acceleration term, which is the same idea. Somebody sitting here, what would they see you doing in accelerating? If you're just walking in a straight line at constant speed, you're not accelerating relative to the person sitting on here. Okay, so that's 0 in this case. Plug and chug. Alpha cross R minus omega squared R plus 2 omega cross the VREL plus no acceleration relative. And that's just math. 0.2x plus y. No problem. So let's go to D. What do we need to see there? I'll bring this up a bit. And Start with the basic equation, same thing. What is the merry-go-round doing at d plus 2 times omega cross v rel. This is the omega of the merry-go-round. This is our v rel, which in this case we know from up here, as you can see, is 0.75 x in the minus x direction. 0.75 meters per second in the minus x direction. Plus, we have this relative term. We're going to have to talk about that one. So if we start plugging in numbers, here's alpha cross r minus omega squared r for d. That's straightforward. This again will be very straightforward. We have all that information. Now we've got to start talking about this puppy. Okay? For that, let's go up here. So if you're sitting, if a friend is sitting here and you're walking this path, all right, when you're walking this line at 0.75 meters per second, there's no acceleration. When you're walking this path, there's no tangential acceleration, but you have to have normal acceleration to get the circular path. Any curving requires an acceleration in that direction. So we're going at constant speed on a circular path, so this would be, you can express this one of two ways. Minus omega squared r, so an effective omega for how fast you're going around this circular path. Or you could do it as v squared over r. Both work. I'm going to stay with the omega squared r, but there's two ways of looking at it. They both give the same answer. So let's just take this up. We know what we're doing here. And so what's happening here? This term's I kind of blew it up because it's so important. So all of these, the first term's self-explanatory. Here's the relative term. So it's going to be minus omega squared, that magnitude r. All right? So what is omega? V over r. That's why I said we could also do this as v squared over r. You got r squared versus r here. You get the same answer. This form gives us all of our vector information, so I preferred this one. So here I have v, magnitude v over r squared. That gives me my omega squared. Okay? And then this is my vector direction. So minus omega squared r. So that's what we have here. Minus omega is the velocity relative divided by the radius. That's 3. So there's my omega squared. Here's my direction. The minus r comes in. R itself is minus 3. So these signs cancel. Net acceleration is going to be going up. All right, so from here, it's just run the numbers, and there's our answer. 0.6x plus 0.1875y meters per second squared is the acceleration of the person walking on the merry-go-round at D. And we'll end this one right there. Catch you soon.